I'm showing this for the video. I want to show it on the projector. So everyone got the same correct answer. I think the important thing at this point is to make sure you have the skill that when you read the question, you immediately start thinking, what units do I want my answer in? Grams per mole. So this is like a lot of the problems we've done in this chapter. We use the equation for the information that we've just studied to rearrange and find the concentration. In this case, it's molar, 0.00147 moles per liter. So now I thought about this. My solution was made of 72.4 milligrams per 100 mils. There's 1,000 mils in a liter, so I now have that changed to liters. 1 liter was 0.00147 moles, and 1 gram is 1,000 grams. So when I look at the units that don't cancel, I'm left with grams per mole, 493 grams per mole. And then you always ask yourself, is this a reasonable answer? And the answer is yes, it's reasonable for a carbohydrate. If you came up with an answer here like 0.02 grams per mole, would that tell you something's wrong? Because hydrogen is 2, and a carbohydrate's a lot bigger molecule than hydrogen. Now, when I worked this out, I kind of did it all in one fence post. Many of you might have taken this molarity and just multiplied by the 100 milliliters to get moles and then divided by the mass. And it's the same math, just done in kind of a different order. Okay, any questions on that one? So now we'll talk about the concept that will lead us into the kinds of problems that were at the end of the homework assignment that's now due later this evening. And Hunter, this addresses the question you had asked about how to do that problem, even though Wiley Plus had the wrong answer. So when we think about the problems we've done up until now, you've been reading questions and they said things like a molecular compound or a non-volatile compound. But none of the examples that we used ionic compounds up to this point. And there's a reason for that. What happens to ionic compounds when we dissolve them in water? They break apart into their ions. And remember, colligative properties are about the number of particles, not what the particle is. So what element, what compound the particle is, whether it's a molecule, an atom, or an ion, they all count the same as a particle. So when you have something like sugar, which is a molecular compound, you put 1 mole of sugar in your solution, you get Avogadro's number of particles, that number of molecules. But when you put sodium chloride in there, an ionic compound, it breaks apart and it gives you sodium ions and chloride ions. So you get Avogadro's number of sodium ions and Avogadro's number of chloride ions, so you get double the number of particles. So effectively, you have twice as many particles, so you would expect to get twice as much colligative property. And that's why we ignore the ionic compounds when we're first introducing the concepts. Calcium chloride. You get a calcium ion and 2 chloride ions. So you get a 3-for-1 sale. You get Avogadro's number of calcium ions and double that for the chloride ions. What would I get with lithium phosphate? What is lithium phosphate? Anybody? Li3PO4. So you get 3 moles of lithium ions and 1 mole of phosphate ions. I do not get phosphorus or oxygen. Okay, it breaks down into its ions. It does not break down into its elements. So, with this going on, in really dilute solutions, we see exactly what we would expect. We see that we get 2 particles for sodium chloride, we get 4 particles for lithium phosphate. However, when things get more concentrated, sometimes As you have a lot of ions in solution, those ions get closer together and they act as though they're still kind of hooked together. Sorry, was there a question back on that page? Oh, how long have I been talking without the overhead? Several pages. Hang on.